Imagine standing completely still. Your feet are planted on solid ground. The air around you feels calm. Nothing vibrates. Nothing rushes past you. Now here's the strange part. At this exact moment, you are moving at over 1,000 miles per hour, spinning with Earth's rotation. At the same time, you're traveling around the sun at nearly 67,000 miles per hour. And together with the solar system, you're moving through the galaxy at an even greater speed. Yet, you don't feel any of it. No wind. No motion. No sense of movement at all. So how do we know this isn't just a story we've been told? How do we know Earth is actually moving? And not just an idea passed down through textbooks and classrooms? That question isn't silly. In fact, it's one of the most reasonable questions a human can ask. Because for most of history, people believed exactly what their senses told them. That Earth was still, unmoving, and central. And honestly, based on everyday experience, that belief made sense. So the real mystery isn't why some people doubt Earth's motion. The real mystery is this. How did humans ever figure out the truth in the first place? Not with satellites. Not with computers. But with simple tools, careful thinking, and experiments so clever that many of them are still used, in one form or another, today. In this video, we're going to walk through those experiments. Step by step. Calmly. Without debates or beliefs. Just observations, measurements, and physical evidence that anyone can understand. By the end, you won't just know that Earth is moving. You'll understand how we know. And once you see that process, the arguments claiming otherwise quietly fall apart on their own. Let's begin. For most of human history, people believed Earth was completely still, solid, unmoving, and placed at the center of everything. And honestly, that belief makes sense. When you stand outside, the ground beneath your feet doesn't shake. You don't feel like you're spinning. You don't feel like you're racing through space at thousands of miles per hour. It feels like Earth is stationary. So when modern science tells us that Earth is rotating once every 24 hours and orbiting the sun at nearly 67,000 miles per hour, the natural question is, how do we actually know this is true? Not because a textbook says so. Not because a scientist claims authority. But because of carefully designed experiments, many of them centuries old, that produced results so precise they still power modern technology today. In this video, we'll walk through those experiments step by step, slowly, clearly, and without hype. No debates. No mockery. Just evidence. Section 1. Why Earth feels still. Before talking about experiments, we need to clear up one important thing. If Earth is moving so fast, why don't we feel it? The answer comes from basic physics. Specifically relative motion and inertia, concepts formalized by Isaac Newton. Here's an everyday example. If you're inside a smoothly flying airplane at cruising altitude, you can stand up, walk down the aisle, pour a drink, or toss a ball straight up, and it comes right back down into your hand. Even though the plane is moving at 500 miles per hour. Why? Because everything inside the plane, you, the air, the cabin, the ball, is already moving together at the same constant speed. Motion at a constant velocity doesn't announce itself. Earth works the same way. The ground, the oceans, the atmosphere, and your body are all moving together. To detect motion, you need external reference points, something outside the system. That's exactly what astronomers figured out how to use. Section 2, Stellar Aberration, the first direct CLUE, 1720s. In the early 1700s, astronomer James Bradley was trying to measure something called stellar parallax. Parallax is the slight shift in position of nearby stars caused by Earth moving around the sun, similar to how your thumb appears to move when you close one eye, then the other. Bradley built an extremely precise telescope, fixed vertically, and observed a star called Gamma Draconis over an entire year. But instead of the tiny back and forth motion he expected, he saw something else. Every star he observed traced a small circular path in the sky, always repeating annually. This phenomenon became known as stellar aberration. So what was happening? Light travels at a finite speed. As Earth moves through space, incoming starlight appears slightly tilted, just like rain seems to fall at an angle when you're walking forward. Bradley measured the shift, about 20 arcseconds. And when he calculated Earth's orbital speed using that angle, it matched perfectly. If Earth were stationary, this effect would not exist. This was the first direct observational evidence that Earth is moving around the Sun. Section 3, Aries Telescope, Testing the Light Itself, 1871. More than a century later, astronomer George Biddell Airy asked a deeper question. What if stellar aberration is caused by the telescope itself? To test this, Airy filled a telescope completely with water. Why water? Because light travels slower in water than in air. If aberration were happening inside the telescope, the angle should change. So Airy observed the same stars again. The result? No change at all. The aberration angle remained exactly the same. This proved that the effect occurs before light enters the instrument, due to Earth's motion through space. This experiment helped eliminate older ideas about light requiring a physical ether, and later became consistent with Einstein's relativity. Instead of undermining physics, it strengthened it. Section 4, Michelson, Morley, When Nothing Was Found, 1887. One of the most misunderstood experiments in science history is the Michelson-Morley experiment. Albert Michelson and Edward Morley were trying to detect Earth's motion through a hypothetical medium called the luminiferous ether. They used an interferometer to split light into perpendicular paths and looked for changes caused by Earth moving through this ether. They found nothing. No ether wind. Some people take this to mean Earth isn't moving. But that's not what the result meant. What it actually showed was something far more profound. There is no absolute frame of rest. The speed of light remains constant for all observers. This result directly led to Einstein's special relativity. Today, this isn't abstract theory. GPS satellites must correct for both special and general relativity, effects caused by Earth's motion and gravity. Without those corrections, GPS errors would grow by several miles per day. Your phone works because these experiments were right. Section 5, Everyday Proofs of Earth's Rotation. 1. Foucault's Pendulum. In 1851, physicist Léon Foucault suspended a long pendulum in Paris. As it swung freely, the direction of its swing slowly rotated over time. The pendulum wasn't turning. Earth was rotating beneath it. The rate of rotation depends on latitude, exactly as physics predicts. You can still see working Foucault pendulums in museums across the United States today. 2. The Coriolis effect. On a rotating Earth, moving objects deflect. To the right in the northern hemisphere, to the left in the southern hemisphere. This explains why hurricanes rotate the way they do, global wind patterns, long-range artillery and aviation navigation. Meteorology literally fails without Earth's rotation. 3. Gyroscopes and modern navigation. Modern aircraft and submarines use ring laser gyroscopes. These devices detect Earth's rotation directly, about 15 degrees per hour. They use light interference to measure rotation. No assumptions. No beliefs. Just physics. Section 6, Orbits, Satellites and Eclipses. Satellites stay in orbit because Earth is moving. Geostationary satellites remain fixed over the same point on Earth only because they match Earth's rotational speed exactly. Solar eclipses, lunar eclipses, and planetary alignments are predicted decades in advance using equations that only work if Earth is rotating and orbiting the Sun. Miss the motion, and the math collapses. Conclusion: why this matters. Science doesn't ask for belief. It asks for consistency. Earth's motion isn't accepted because someone said so, it's accepted because independent experiments, across centuries, using different methods, all point to the same conclusion. Understanding how we know this matters more than the answer itself. Because it shows how humans uncover truth, not through intuition alone, but through observation, testing, and reason. If this exploration helped clarify things for you, consider subscribing for more deep dives into science, philosophy, and the deeper patterns behind how we understand reality. Stay curious. And keep questioning, carefully.